Okay, let's start the second presentation, and the title is the recent developments in learning quantum phenomena. The speaker is Professor Jerry Lee, and I saw you worked before on the Microsoft, and now is in the University of Washington. Let's welcome.
Oh yeah, thanks. So this is a talk. So just at a very high level, the goal of this talk is to give a relatively gentle introduction to folks who sort of understand TCS kind of techniques to the sort of basic concepts and techniques in learning quantum states. This includes sort of these sorts of things. So there's sort of corollaries. First of all, if you're a quantum person, I'm not going to be using this sort of bracket notation for vectors. Please don't kill me. And the second is if you know representation theory, there are parts of this that might be boring for you, but my apologies. But yeah, with these caveats, this is sort of the general outline of the talk. I first like to define the basic ideas of quantum learning. Then I'd like to tell you about sort of the power of this sort of entangled measurements. But then I'll tell you a little bit more, and this is sort of previous work. Mostly what I've worked on is understanding the cost of entanglement and what happens when you're not allowed to use entangled measurements. So I'll tell you about what all these things mean, hopefully, in a bit. So let's just get started. Okay, so what is quantum learning? So the way I define it is, the basic question here is how can we learn about quantum objects and phenomena, right? From a scientific point of view, given that the world is, at least to the best of our knowledge, fundamentally quantum, this is probably one of the most basic scientific questions just out there. Right? So the basic premise is let's say there's some scientists in a lab and they run some experiment, right? And they do some sort of quantum procedure, and the outcome of this is some unknown quantum state rho. Okay, and the scientist wishes to learn about what this quantum state rho is. This is going to tell them about whatever phenomena they're interested in. There's some basic questions. Maybe they just want to get a classical description of this object. Maybe they have a guess of what this object ought to be, and they just want to test if it's equal to it. Or maybe they just need to know some sort of classical statistics about this object. Okay, and I'll tell you what all these things mean in a second. Okay, now we're going to be interested primarily in this sort of online setting, right? So we imagine that in this lab, you have some experimental setup. You can run some experiment and you get a copy of your state, right? Then you can reset everything and get to do it again. So as a function of time, right, you sort of do an experiment, you get a copy of your quantum state. Then you can, reset everything, do the experiment again, get another copy of the state, and so on and so forth. And the basic question that we're interested in understanding, this is sort of the sample complexity of the problem, is how many copies of the state, does the scientist need to produce to learn whatever they want to learn about the state? Okay, so this is the quantum analog of sort of sample complexity. And again, this is a very well-motivated question from a number of perspectives. Again, from a sort of scientific point of view, given that the world is probably physically, fundamentally quantum, if we want to learn stuff about the world, we're going to have to sometimes learn about its quantum behaviors. It's also useful as a subroutine for the verification of quantum computation. Right, the state of a quantum computer is some quantum state. If you want to understand if it's in the right state or not, we're going to have to sort of learn about it. From a mathematical perspective, also very natural. It's the sort of natural non-commutative analog of classical distribution learning and testing. And also, it's going to have some implications for quantum advantage, which is something I'll delve into a little bit at the end. Okay, so now let me actually define these things. Okay, so recall what a classical distribution is. So this is going to be a very overly detailed definition of this. So recall that a distribution over D elements, any probability distribution, this is just specified by some probability vectors. So specifies some P in RD with property that is not entry-wise non-negative and it sums to identity. Right? So it's like P is some histogram. Right? And again, a sample from this distribution is just you get the ith element with probability P sub I. Okay, very nothing's happening. Now, quantum distribution is just sort of the natural matrix analog of this. So now it's known as a mixed state, not a distribution. And now it's specified by a complex D by D matrix, and it's over the spectrahedron, meaning that instead of having this property, it is now positive semi-definite, and the trace of rho is 1. So in other words, its eigenvalues are all non-negative, and they sum to 1. So you can sort of see there's this analog between the classical and quantum settings. And indeed, to make this super formal, by the spectral theorem, this sort of standard stuff, right? We know that we can write a row as some sort of rotation matrix times some diagonal matrix in the middle times, the dagger of this rotation. So in other words, the object in the middle, right? This is the diagonal matrix of eigenvalues. These are non-negative and they sum to 1. So this is some like encoding of a classical probability distribution. And what's happening is that you're somehow rotating it in RD. Okay? So this is just really saying that this is like sort of, again, the right sort of matrix analog of classical learning. Now there's a couple of other key differences. The first key difference is that of measurement. So in the classical world, you get samples from your probability distribution, right? I get element I with probability p sub I. But quantumly, you don't just sample. You have to actually specify how you interact with your quantum state. You have to specify a measurement M. Okay? So formally speaking, what a measurement is, it's a little bit complicated, but it's actually not too bad, I think. But it's a lot of words. So a measurement is just a collection of d by d matrices. So M sub 1 through M sub L, where the number of matrices can be arbitrary, as long as they satisfy the following two properties. First, each individual matrix is PSD, and they form a partition of the identity. Okay, so they sum to the identity matrix. And for physics reasons I'm not going to get into, this collection is known as a positive operator valued measure, or POVM. Okay, so when I say a POVM for the rest of the talk, I mean a measurement. Okay? And for most of the time, we're going to assume that each MI is a rank 1 matrix. It turns out that this is without loss of generality for us, mostly. So in other words, we can think of most measurements as just being of the form, Wi times xi star, right, for some unit vector xi and some weight, non-negative weight wi. Now, if I specify a measurement, what happens when I measure my state rho in this measurement? The outcome is I get one of these matrices back. I get one of these measurement outcomes back. And the probability of getting the ith measurement outcome back is exactly the trace inner product between rho and M sub I. And you can verify that this is a valid probability distribution over M1 through M sub L. This is a very simple calculation. And when in the special case where MI is rank 1, you get this nice sort of quadratic form with your vector xi. Okay? So hopefully this makes sense. And you can check, indeed, that if everything is diagonal, then this actually recovers classical sampling. So this is a strict generalization of the process of classical sampling. But again, there's this notion of like, the algorithm has to do something to get a sample in the quantum case. They can't just like press a button. There's a sort of additivity here. I should also say that when you do this process, your state rho collapses in some predictable way. But for the purposes of this talk, it's not super important, and I'm going to sort of ignore this fact. But what will be important is that when I measure, essentially what happens is I'll think of rho as being destroyed. So if I do a measurement, I think of rho as being destroyed by this measurement. Okay, so I can apply a measurement to a copy of rho, but if I want to do another measurement, I'll have to use a fresh copy of rho, for instance. Okay, so hopefully this makes sense. This is not technically true, but for the purposes of this talk, it's close enough. Okay? Are there any questions so far? Okay. So now I've told you how you can actually define what a quantum distribution is and how to interact with them. Now we can state a bunch of like natural quantum learning and testing problems. So we can do so by analogy to the classical setting. So here are some basic problems in classical learning and testing. Right? I have n samples, so some unknown distribution p. My goal is to infer some property of p, and there's a bunch of these which are well studied. For instance, one which is well known is like uniformity testing. I test if p is a uniform distribution or far from it. More generally, I can test if p is equal to some given distribution q or far from it. And there's also just the learning problem. It just outputs some description of p to some error epsilon. And all these statements are going to be with high probability. Right? In the quantum learning setting, this is exactly the same almost. Right now I'm given n copies of unknown quantum mixed state rho, and my goal is to infer some property of it. So just how there's a notion of like the maximally spread distribution, there's also a notion of a maximally sort of spread quantum distribution. This is known as the mixed state. And so you can have mixedness testing. And just like how there's a notion of testing equality between two classical states, there's also sort of the quantum analog of this, which is known as state certification. And the learning problem is known as state tomography. Okay? So hopefully these things more or less make sense. Now there's a second key difference between the classical and quantum settings, which is this issue of entanglement. Okay, which is that formally speaking, n copies of a mixed state is just one copy of a much bigger mixed state, this sort of tensor state, rho tensor n. This lives in a much higher dimension, but from a purely mathematical point of view, there's no distinction between the two. So in other words, if I have 3 copies of a state or n copies of a state, this is just one copy of a bigger state. And one important thing is that rather than measuring each individual copy of rho one at a time with their own measurements, I can apply one joint measurement to this entire mixed state all at once. Okay, such a measurement is called entangled, and it turns out that they're very powerful. Okay. So this is what I'd like to get into in the second part of the talk. Just explain why this is useful. Because it's sort of weird intuitively why it'd be useful to have entangled measurements, because the states themselves are not entangled. These are, each copy of rho is non-interacting with each other. We're assuming they're sort of independent copies of the same rho. But somehow it's supposed to be the case that even though the rhos themselves are not entangled, it's helpful to have an entangled measurement. And for this, unfortunately, I need a brief detour into representation theory. So the next couple of slides might be a little bit of gibberish, but I'll have like a summary that hopefully makes sense at the end. And this gets into this issue, this classic result known as Schur-Weil duality, right? And it's actually relatively easy to motivate what's happening. Suppose I'm interested in estimating some property of rho's spectrum. So I'm interested in estimating something that only depends on rho's eigenvalues. It doesn't depend on its eigenvectors at all. Okay? Then if I design a measurement of rho tensor n, it should obey the following 2 properties. First, it shouldn't care if I permute the copies of rho, right? Because rho tensor n, if I permute the n copies of rho, is the same object as before. So whatever measurement should be invariant under this sort of group action. And the second thing is that it should also be invariant to applying a shared unitary across all n copies of rho. So if I fix some u and I apply it to all n copies of rho, this doesn't change the spectrum of rho at all. So my estimator should output the same result, for rho tensor n and for u dagger u tensor n. Right? So hopefully this makes sense. And the point is that you somehow want to come up with the maximally useful measurement that is sort of invariant under these 2 sorts of symmetries. And it turns out the way you can formalize this is with the Schur-Weil duality. Yeah. I just mean like the outcome of the measurement should be the same. Like if I measure, well, if I want to do a measurement, well, there's a formal sense in which this is true for this. Like the optimal measurement, you can first do Schur-Weil sampling, weak Schur sampling, and then do your measurement. As long as you're estimating some property that only depends on rho's eigenvalues. Yeah, hopefully I'll get to that in a second. Okay, but this sort of motivates what Schur-Weil duality is saying. So, okay, if you're familiar with representation theory, right, both the symmetric group S sub n, which is the group of permutations on n elements, and the unitary group, they have a natural action on this sort of tensor space. And I'm going to define these 2 associated representations of these groups. So P is a representation of Sn, Q is a representation of UD. So P is a homomorphism from Sn to a set of like group actions or linear maps on CD tensor n. And the way you actually do this is actually very straightforward. You define the action on any tensor vector and then just linearly extend it. So for any permutation pi and any tensor vector x1 tensor x2 dot 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 xn, I'm going to find the group action or the action of pi on this vector to be just what happens if I apply the inverse of the permutation to this vector. Okay, and then again I extend this to all vectors by linearity. And similarly for any q, I define the action of the representation of q on x1 tensor xn by just applying u to each individual copy, and again I extend this by linearity to all vectors. Okay, so these are associated representations, and the sort of key fact is that both of these representations have some sort of direct product structure, and they have irreducible representations, and it turns out they're both naturally identified with some combinatorial structure, and moreover, because these 2 sort of actions commute with each other, and this is very crucial, their joint action has some shared joint structure. Okay, and this is formalized by the famous Scherr-Weil duality, which is stated as follows. Okay, there's a lot of symbols here. It says that the joint action PQ is isomorphic to a direct product of this, whatever this is. I'm not really going to define what these things are, but there's sort of a couple of key things. First, arguably, actually, the most important for the purpose of this talk is what this lambda is. So this direct sum is indexed by partitions of n into at most d parts. What does that mean? It's a set of all like vectors, lambda, of non-negative, non-increasing integers that sum to identity, so sum to n, excuse me. So sum of lambda I is equal to n, so they're a way of breaking up n into k parts, and the number of parts k is supposed to be less than d, the dimension. So this is how you index into this direct sum. And then I'm not going to really tell you what p and q are. P is this is spect module, and q is some matrix polynomial. Okay. If you didn't really understand this, it doesn't really matter. The point is that at least for our purposes, the key point for us is that what that statement implies is that there's some fixed like global unitary, which I denote U sub Scherr, which acts on the tensor space, so that for any d by d matrix, if I apply this unitary to row tensor n, I get that this matrix is now also decomposed as a direct sum. Okay, and what this is just equivalent to saying that after I apply this U Scherr, my matrix has a block diagonal structure. So each block is indexed by some lambda, one of these partitions, and in fact, within each block, it also has some nice block diagonal structure. Okay, and this is true. This is some fixed unitary that doesn't depend on row. This works simultaneously for all row. So this fixed matrix, like simultaneously block diagonalizes all row tensor n. And this is important for us because that means that any measurement should also be block diagonal with respect to this block diagonal. There's no reason not to commute with this structure that holds for all row tensor n. So in this basis, the optimal measurement should be block diagonal. And this is exactly what weak Scherr sampling says. Right, so weak Scherr sampling first rotates rho with this sort of Scherr transformation, this U sub Scherr. And then let pi denote the projection onto the coordinate subspace indexed by lambda. So pi lambda is just a projection onto this coordinate subspace in the Scherr space. Right, and pi eta is just projection onto this space. Sorry. Okay. And then you measure in the measurement given by this sort of set of projections which span all of RD. So this is weak Scherr sampling. Again, the idea is just simply once you've applied this rotation, you should just measure in this sort of coordinate basis because any row tensor n is block diagonal, so you should also be block diagonal. And this is true, indeed, folklore, but there's also a proof in John Wright's thesis that suppose we're interested in measuring such a spectral property of rho, some property that only depends on its eigenvalues, you might as well do weak Scherr sampling first. Okay, so it's literally optimal for such properties. Okay, and this also explains why it's useful to have entanglement. Because this U sub Scherr, this is some rotation in the overall space in this CD tensor n, which means to apply this rotation necessarily is an entangled measurement. Like the overall measurement must be entangled. So this is why entanglement is useful. Okay, so hopefully that made at least some high-level sense, even if you don't know representation theory. Now I'm going to very briefly discuss like how one uses this actually, how actually one analyzes Scherr sampling. The reason why Scherr sampling turns out to be useful, it turns out that so when you perform Scherr sampling, right, the Scherr basis or the Scherr measurement is indexed again by these lambdas, right? And it turns out that the lambda that you get, the partition that you get, it acts sort of like a quantum analog of like a histogram of a distribution. In particular, it's well known, for instance, that if alpha denotes the eigenvectors, eigenvalues of rho in decreasing order, that if I take, a draw from the Schur-Weyl distribution, so I draw one of these histograms, or these partitions, and I just divide it by n, this quantity actually approaches the eigenvalues of lambda, of rho, okay, asymptotically. So this is why there's some like combinatorial connection between like weak-Schur sampling and these sort of spectral properties. It actually gives you some sort of, it's actually biased, but the expectation tends to alpha as n goes to infinity. And the variance can also be controlled and stuff like this. But actually analyzing the sort of non-asymptotic behavior of this this requires, combinatorial understanding of these partitions and how they behave, and I'm not really going to talk too much about this. But if you're interested, for instance, you can see John Wright's thesis. He has a really great exposition of these sorts of things. And by doing a lot of work actually after weak-Schur sampling, but still using weak-Schur sampling as a base, you can actually use these sorts of ideas to obtain sort of the right rates for a number of problems. So these are, for instance, some a rate obtained by O'Donnell Wright, saying that for mixedness testing, you need d over epsilon squared copies to solve it using some sort of entangled measurement. And also for tomography, right? Tomography was a problem of learning my state. It turns out the right answer is d squared over epsilon squared. And these are all in trace norm. Okay? And there's many other settings as well where one can use this. So by using these sorts of techniques, as well as other sorts of like entangled measurements, you're able to obtain fairly striking results actually for a number of problems, including some of these listed below, amongst others. Okay? So, I mean, that's cool, I guess. So what am I still doing, I guess? It turns out that, unfortunately, while these entangled measurements are very powerful, they also come at a fairly heavy cost, particularly in terms of practicality and the ability to actually run these measurements on near-term quantum computers. And the explanation for this is like fairly straightforward. So recall that an entangled measurement is a measurement on the joint state rho tensor n, right? But what is rho tensor n? This is just n copies of my mixed state, right? So in an ideal world where we have perfect large-scale quantum memory, a copy of rho comes in, I just store it in my quantum memory. Another copy of rho comes in, I store it, and so on and so forth. At the end, I have rho tensor n, and I can apply my joint measurement, and I'm happy. But this is really not the case. We don't have the ability to have this large-scale quantum memory. Right? So much more realistic, actually, is a setting where a copy of rho comes in, it's going to disappear, it's going to decohere very rapidly. We can't wait for all the other copies of rho to come in. So the best thing we can do is just measure that copy, as it comes in. It gets some classical information, but the measurement destroys all the quantumness. So we get to store some classical information about rho, and then the second copy of rho comes in, we can measure it again, get some more classical information, and at the end we get to do some sort of classical processing on the outcomes of these measurements. But now we don't get to do these nice joint measurements. Instead, we have to measure one copy of rho at a time. Although notice, and this will be important later on, that these measurements could be adaptive. So for instance, when I measure here, I get some classical numbers, and then potentially this second measurement could be chosen adaptively based on what I got here. Okay? So the basic question is, how powerful are these entangled measurements? If you have to measure each copy of rho one at a time, like, do you pay anything? Maybe if you're really clever, you can come with like algorithms that match the statistical rates of these entangled measurements without requiring quantum memory. Unfortunately, what we showed, so in work with Bubek and Sitan Chen, 4 years ago, we showed that there are some settings, some natural settings, in particular mixedness testing, where there are asymptotic separations between what you can do with and without quantum memory. So if you don't have quantum memory, if you're in this setting, you perform strictly worse, information theoretically. And kind of interestingly, The techniques here really are not really quantum in nature. They're much more based on lower bound techniques initially developed for like online learning and these sorts of things. Okay? And since then, we've actually been able to expand these sorts of lower bounds to many other settings, building upon these sorts of techniques. So here was the same table as before. And now we actually have a number of lower bounds for a bunch of these settings. So I'm not going to, I don't expect you to like parse exactly what these things mean, but I want you to take away, there's some sort of key takeaways from this table. The first qualitative takeaway is that at least in all these settings we considered, there is an asymptotic improvement from having quantum memory, right? The numbers here are strictly smaller than the numbers here. Okay? And the second thing is that some cases, for instance, like these rows, this advantage can be exponentially large. So there can be an exponential advantage from having entanglement. So somehow the fact that you can do these sorts of more complex quantum operations turns out to be very, very important, okay, to obtain efficient statistical rates. And I should mention, this is in many ways a very self-centered table. This is sort of the problems that I've cared about. But there's a lot of people working on related questions. If you're interested in seeing sort of a more sort of actual overview of the literature, there's an excellent sort of survey here that you should be, I encourage you to look at. This looks at, the survey covers these questions as well as many other interesting questions in quantum learning and testing. Okay? So this is a brief sort of detour, but in some sense, all these bounds are just sort of bad news, right? Like when you think about it. They're really just saying that we can't, because we don't really have large-scale quantum memory, we don't have persistent quantum memory, a lot of these quantum learning tasks cannot be performed efficiently, right? This is what these lower bounds are saying. And to some extent, this is true. This is what we're showing. We are showing indeed these sorts of lower bounds. But there's a sort of cool thing that we were able to do by sort of flipping this around. Because it's true, our lower bounds give these tasks that provably and unconditionally, like purely information theoretically, cannot be solved efficiently unless you have quantum memory. Now, while I mentioned, quantum computers don't have large-scale quantum memory, they have like a little bit sometimes. They have like medium-scale quantum memory. Which means that if we can somehow beat one of these lower bounds on a real quantum computer using the small amount of quantum memory they have, then somehow this quantum memory must be used in a fundamental sense. This is some sort of fundamentally quantum thing that this computer is doing that cannot be classical in nature. So in other words, this is a way of demonstrating that these quantum computers are fundamentally quantum, which is a way of demonstrating quantum advantage, right? This is something that demonstrates that this quantum computer is not classical. It's strictly more powerful than classical, which is pretty cool. And it turns out we were actually able to do this. So I'm going to skim over many, many details. But we were able to carefully design a sort of learning task such that with like a small amount of quantum memory, you can solve it efficiently. And if you don't have quantum memory, you need exponentially many samples. And what we're able to do is we're able to perform these measurements on a real quantum computer, Google's quantum computer. And okay, we feed them through some sort of learning algorithm. In this case, we use a neural network. And the point is this third graph here. Okay, so on the x-axis, this is the system size, the number of qubits, of the problem. And the y-axis, this is the number of experiments that you need to get 70% accuracy on this task. Okay, and this gray dotted line here, this is the completely rigorous, with like all the constants and everything worked out lower bound, such that if you don't have quantum memory, you must be above this bound. You must be above this line, right? And the key point is that our algorithm, whatever it's doing, maybe its measurements are kind of noisy, maybe the neural network doesn't work perfectly, but whatever it's doing is getting below this line, which means that this is a demonstration of quantum advantage, which is pretty cool. And this is work that we published in Science a couple years ago, where we demonstrated this, and I would argue that this is perhaps one of the first unconditional demonstrations of large-scale quantum advantage sort of in any setting ever, which I think is pretty cool at least. Okay, so now I'd like to spend the remaining time telling you how we actually prove these sorts of lower bounds, or at least giving you sort of a high-level idea. I'm going to try to do so by giving you a relatively simple example, namely for shadow tomography. So unfortunately, the problem itself is not the easiest to state, but this is a setting where the proof is the easiest, which is why I'm going to try to explain it here. So what is shadow tomography? The problem is actually not that unnatural. So this was first introduced by Scott Aronson back in 2018. So here we have a collection of M observables. So these are matrices with the property that their spectral norm is at most 1. Okay, for all J being 1 through M. And now your goal is the following. You're given n copies of some unknown state rho, and your goal is to estimate the trace inner product of O sub j rho for all j to additive error epsilon. Okay, and the goal is to do this with as few copies of rho as possible. Okay, so the question again is how large does n have to be? So, okay, what do we know? Well, in really nice work of Badescu and O'Donnell, it turns out that there's an estimator that uses entangled measurements that succeeds with high probability when n is this. So the exact rate is not super important. The qualitatively important thing is that everything here is logarithmic in M and D. Okay? And this, I should say, this builds upon like a long line of work by like Aronson and Rothblum and many others. So our result is a lower bound. Our result says that if you don't use entangled measurements, so I should, crucially this uses entanglement. What we show is that if you do not use entanglement, your rate has to be the following. In particular, the key point is that now your rate is polynomials, linear in M and D, as opposed to polylogarithmic. So in other words, any estimator for this problem that doesn't use entanglement, that doesn't have quantum memory, is provably exponentially worse statistically. Okay, so this is what I'd like to prove, or this theorem is what I'd like to more or less prove in the rest of the talk. Yeah. Okay. So that's for classical shadows. But for classical shadows, they pay a D factor. So classical shadows is their measurement is not allowed to depend on. Oops.
I'm just saying it's not 1/4.
Okay, there's some like min of this and D over epsilon squared. But in the regime where I guess M and D are very large, you're right. In fact, we actually have recent work that improves this in that regime. But yeah, you're right. This is a slight oversimplification. But the point is that, okay, if I'm interested in dependence on M and D, these dependencies are quasi-polynomial, or sorry, polylogarithmic. Okay. So how do we prove these bounds? Or this lower bound? So again, the main technical challenge of proving these lower bounds is dealing with this adaptivity that I mentioned before, right? The key point is that, okay, I have my measurement. I perform my first measurement on my state. I get some classical outcome. And now I can use the outcome here to design my next measurement, and so on and so forth, right? Now I have measurements x1 and x2. These are measurement outcomes. I can use both of them to design my third measurement, and so on and so forth. So how do we deal with the fact that the measurements can be adaptively chosen? And this is really a key technical challenge because, okay, oversimplifying things somewhat, it turns out that most of the time, if you don't have adaptive measurements, like if the measurements are fixed ahead of time, you can use relatively standard techniques from like statistical learning theory and statistics to get these bounds because the measurement outcomes are independent. But when you have adaptivity, all these independent things break completely, and so these bounds are typically much more challenging. But such a lower bound, of course, is also important if I want to rule out, if I want to prove quantum advantage. I really need to rule out any algorithm that doesn't use quantum memory. Okay, so how do we do this? Well, the first is like a fairly simple conceptual idea. And this is sort of inspired by literature on bandit lower bounds. But what we do is we introduce this notion of a tree estimation of any unentangled learner. So we take a way of like associating any estimator or algorithm with some learning tree. Okay, and I think the easiest way to explain how we do this is just through an example. Okay, so consider some estimator that doesn't use quantum memory, but which uses n copies of my state. Okay, so initially, before it's measured anything, it doesn't know anything. So I'm going to represent this with a node with an empty knowledge string. Okay. Now, when it measures the first measurement, well, it doesn't know anything, so it has some fixed measurement, let's say. So let's say it uses the following 4 measurement POVM. Okay. So it measures the first copy of rho with this 4 measurement POVM. And let's say that the measurement outcome is the second one. Then the knowledge of my algorithm is exactly that I went down this edge, right? So based on this information, but this information alone, it must now choose the next measurement, right? So let's say if it measures the first measurement to be x2, it chooses the following 3-element POVM. And let's say again, it measures the third element. Well, then my measurement information is literally that, the second measurement came up this, and this first measurement came up this. So based on this information, but again, this information alone, it must choose the next measurement it wants to make. And so on and so forth, until it's measured all n copies of rho, at which point it ends at some leaf node. And the leaf node is indexed exactly by the sort of root to leaf path. And all the algorithm knows is which leaf node it ended up at. Right? This is exactly all the information the algorithm knows. And based on this information, and again, this information alone, it must decide, whatever it has to decide. Okay, so hopefully this makes sense conceptually. And the key parameter here is the depth. So I make no assumptions about the sort of fan out of my tree. The fan out could be arbitrary because there could be arbitrarily many elements in the POVM. But every time I do a measurement, I think of it as destroying a copy of rho. Right? So I need n, if I have n copies of rho, then the depth of my tree can be at most n. Okay? So this is the key parameter here. Okay, so how do I reason about such distributions, or these such tree representations? Well, suppose my underlying state is rho, and suppose I've reached some intermediate node in my tree u, and it's indexed by some string of things it's seen so far, x1 through xl. What are the transition probabilities? Let's say at this point it chooses to do the following 2-element POVM. Okay, this is an oversimplification. What's the probability that it transitions to here versus here? Well, I've already told you. It's just the probability that I measure one outcome or the other. Right? The probability I measure this is just the trace inner product of rho with this, which is just this quadratic form. Right? And again, the probability that I transition here is just this trace inner product, this quadratic form. Right? And notice this is very simple. In fact, this expression doesn't depend, this expression doesn't depend on this. It just depends on rho and y1. So it's actually a fairly simple, relationship to define these transition probabilities. So this has the following corollary. Suppose for some fixed learning tree, so for some fixed algorithm, I let t sub rho denote the distribution of which leaf node it's likely to end up at if my unknown state is rho. Okay? So in other words, I have fixed some learning trees, I've fixed some algorithm, I feed it n copies of rho. T sub rho is just a probability that I land at any sort of leaf node. Right? And again, the leaf node is the only information the algorithm gets, whichever leaf node it ends up at. Then we have the following corollary. If I take any leaf node and it's indexed by some root to leaf path x1 through xn, then the probability of reaching that leaf node is just a product of the transition probabilities. Right? So it's just the product from 1 to n of these individual transition probabilities. So actually this expression is, okay, it's a big product, but it's actually not that nasty in the end, which is pretty nice. Okay, hopefully this makes some high-level sense. Now, as I mentioned before, any algorithm or estimator, they get exactly one draw from this distribution, right? They run their algorithm, they get their measurements, and they end up at one leaf node. And that is all the information they get, which leaf node they ended up at. That's all they get to know. That is to say, suppose I want to show you that some estimator cannot distinguish between two states, rho and rho prime. Then it suffices to show that these two tree distributions, t sub rho and t sub rho prime, are statistically indistinguishable. Right? So pictorially, right, I have some tree. There's two possible worlds. Either I ran n copies of rho, or I ran n copies of rho prime, and I end up with either t sub rho, or a draw from t sub rho, or a draw from t sub rho prime. And I get exactly one draw from one of these two distributions. And if my algorithm is going to distinguish between rho, rho, and prime, I need to distinguish a draw from t sub rho between a draw from t sub rho prime. So the question is whether or not these two distributions are distinguishable or not. If they are not distinguishable, then the algorithm cannot tell the difference between rho and rho prime. Right? So hopefully this makes sense. Now typically, if you're familiar with, for instance, statistical learning bounds, to prove these lower bounds, it's not going to suffice to just take one pair, rho and rho prime. We're going to typically have to draw at least one of these from some family of possible states. So from some problem-dependent distribution over states. And let's say rho prime. We're going to draw rho prime from some distribution D. So now the question is still really simple, right? So on the one hand, I get a draw from T sub rho. This has not changed. But in the case where it's rho prime, now my like posterior distribution is some expectation, is a mixture of rho prime of T sub rho prime. And now the question is, can I distinguish between one draw from this and one draw from this mixture of distributions? And that's all I need to show, right? Okay, so let me show you how to instantiate these bounds for shadow tomography. So recall, this is a problem, right? I have these observables, they're all bounded, and my goal is to estimate their trace inner product, given n copies of rho. So how are we going to reduce this to this distinguishing problem? Well, we're going to set up some sort of like quantum Lecam's method. So let me tell you what this means. So without loss of generality, I can assume that all the trace of the observables are all 0. They're all traceless. I'm also going to design my family of OJs. I'm allowed to do so. I'm going to have two properties. First of all, the OJs are these orthogonal matrices. So all the eigenvalues are the plus or minus 1. Okay? I'm also going to assume some sort of symmetry in the family. That if O sub j is present, then minus O sub j is present with the same, same cardinality. So I can just always do this by almost doubling the size of my family. And now what I'm going to do is I'm going to construct the following distinguishing problem. In sort of the null hypothesis, rho is just the maximally mixed state, so which is just 1 over d times the identity matrix. So this is what is known as the maximally mixed state. And in the second case, rho is equal to one of these rho sub j's, where rho sub j is equal to this state. So this is the maximum mixed state plus some perturbation, 3 epsilon oj over d. Okay? Where I choose j chosen uniformly random. So this is some distribution over random states. Or some, yeah. And the claim is that if I can solve shadow tomography, I can solve this problem as well. This distinguishing problem. And this is a fairly straightforward calculation, so I'm just going to do this now. So, okay, so these are the two states I've defined. All right, so let's just run our shadow tomography algorithm. In the case of the null hypothesis, we've made it such that all the O sub j's are traceless. So, the true trace inner product is 0. And we get all the trace inner products there at most epsilon, so all the return inner products are at most epsilon. On the other hand, under the null hypothesis, for whichever true j we've sampled, it's a simple calculation that shows that the trace of oj rho j, trace of oj rho j is 3 epsilon. Okay? Which means that since we get these all to error at most epsilon, so for that true j, our shadow tomography algorithm will output something which is at least 2 epsilon. Okay? Which means that we can distinguish. Okay? So hopefully this makes sense. So in other words, if I can solve shadow tomography, I can always solve this distinguishing problem as well. Okay, so now how do I prove a lower bound for this distinguishing problem, distinguishing between H0 and H1? Okay, so fix some learning tree. There are now 2 distributions over leaves of this tree. One is the distribution induced by the maximally mixed, and one is its expectation over T sub rho j's. And again, the estimator gets one draw from either P0 or P1. And we need to, the algorithm, if it's supposed to succeed, needs to distinguish between these 2 cases. Okay, and we will show that the lower bound by the following 2 claims. The first is the total variation distance between these 2 distributions is at most this quantity, n times epsilon, this should be capital N, times epsilon squared times delta, where delta is this sort of nasty thing. It measures a sort of worst case variance of the quadratic form along any direction. Okay? And the second claim is that if I just take the O sub j's to be random, then this quantity delta is very small. Okay? And putting these 2 claims together shows that the total variation distance between these 2 distributions is very small unless n is sufficiently large. Right? Recall that to distinguish between P0 and P1, we need that total variation distance is like constant. And what this is saying is that this is the total variation distance is subconstant unless n is like the inverse of these. Yeah. Okay, so hopefully this makes sense at some high level. I'm not going to prove this. This is a relatively standard this follows some standard techniques in like random matrix theory. So I'm mostly going to show this. This is, I think, more informative for this talk, which I hopefully have time for. Yeah. Okay, so I'm going to try to prove claim 1. And the claim is that I'm just going to look at the light-cleared ratio. So I'm just going to look at the likelihood ratio at any node in the tree. So for any leaf node, it turns out there's actually this likelihood ratio has a pretty nice form. Actually, so the probability under the null, or the null versus the alternate, is actually this sort of big product. So it's an expectation over J. Recall J is uniformly random of this product of 1 plus 3 epsilon xi star oj xi, where these xi's is the sequence, is the xi's I encountered on my root to leaf path. Okay, this is an equality. This just follows from a straightforward calculation. And it's going to turn out that it suffices to show that this likelihood ratio is lower bound, is pointwise lower bounded. So I'm going to show that for every leaf node in the tree, this is close to 1. And this, it turns out, is sufficient to show a total variation bound. Okay? So it's actually kind of surprising, actually. You can show that there's like literally every node in the tree is equally likely to be reached, essentially, using this argument, which is a very strong statement, actually. So xi is a POVM element. So this is like the measurement outcome of the first. Well, I'm assuming here that the POVMs are rank 1. So it's a vector. So the POVM is like x1 transpose, or ket xi, bra xi. It's because I don't care about like the state after measuring. So if I don't care about the collapse state, I can always take my POVM element and decompose it into rank 1 terms. Yeah. So that's why if I cared about the state afterwards, I couldn't do this. But since I don't really care, because I'm not allowed to reuse states anyways, I can always take them to be rank 1. And it doesn't really make a difference, to be honest. Yeah, that's a good question. Okay, so how do I actually bound this? I mean, we're just going to do sort of the obvious thing. So we have this expectation over J. So the problem, right, is that this product is shared across all n terms. So there's some sort of like high degree polynomial in this random variable J. So what we're going to do is we're just going to do a natural thing. We're going to write this as an expectation of an exponential of a sum of logs, right? And recall we only need a lower bound, so we're allowed to by using Jensen's inequality, push this expectation inside the exponential. Okay, and this is nice. Now we have a exponential of a sum of x, expectation of a sum, which is why we did this in the first place. This is much easier to do. Okay, so now this is like a little bit of tricks. So in the first term, all I've done is I've just pushed the expectation inside. In the second one, oh, I apologize. These expectations should not be here anymore. This is the expectation, right? I'm just taking an empirical average. So that's from here to here. From here to here, this is where I'm finally using symmetry. I'm using that, if OJ is in my family, then minus OJ is also in the family. So I'm grouping up my terms. And the reason why I want to do this is now I have log of 1 plus blah and plus log of 1 minus blah, right? And the nice thing about that is that is equal to log of 1 minus blah squared. Right, so this is equal exactly to this. Okay, this exponential should not be here. My apologies. This is exactly equal to log of 1 minus, this quantity squared. Okay, so hopefully that makes sense if you stare at it for a little bit. And then, to finish up, it's fairly straightforward. What we're going to do is we're just going to use a sort of naive bound, lower bound on log 1 minus x, which holds for all x in some sufficiently small range, which you can verify we satisfy. So what we get is that this term, which was originally in the exponential, can be lower bounded by this term. And if you pull the 18 epsilon squared outside, this is exactly this sort of delta quantity before. So this is the thing that's maximized by the delta quantity before. This is in some direction xi, what is the worst case variance of the quadratic form. So this is lower bounded by this quantity here, and then we're pretty much done, right? Because this says that this term I've just simplified here, is at least this x of minus blah. And again, by using a standard estimate on exponentials, I get exactly this as desired. So that's the entirety of the claim. As you can see, it's actually fairly straightforward. And this is, it turns out, already actually tight. So this is this sort of Jensen inequality style approach. And as I mentioned, actually, I guess I didn't mention this, maybe not. But it turns out that like the rate that we get without unentangled measurements from this method is tight. There's a matching upper bound. So actually, for this problem, it's tight. However, it turns out that this is not always tight, because if you think about qualitatively what this is doing, it's really saying that along any edge in the tree, there's a uniform bound on how much information I obtain, which depends on this delta quantity. And that's what this Jensen inequality is doing. And sometimes this is not true. Sometimes you can come up with like settings where there's like one edge that's like actually pretty informative, but if you amortize it along the entire path, it's still not sufficiently informative. So sometimes we have to do sort of path-based analyses, and these are often much more complicated. So some of the first techniques that we had were these sorts of like chain rules that bound TV by these sorts of conditional chi-squared. And this is actually a generalization actually of lower bounds first developed for online learning. And more recently, actually, we've actually been able to directly demonstrate anti-constitutional posterior by just staring at the high degree polynomial. Essentially what happens is if we just, instead of doing any tricks with Jensen inequality, we just like treat this as a high degree polynomial in the OJs and directly bound moments of this high degree polynomial, which is very nasty, but you can do it if you need to, apparently. Okay. So yeah, there's some like high level intuition about like if you choose the right sort of prior, then this polynomial isn't as bad. For instance, if you choose Gaussian priors, there's some sort of like nice self-similar structure that you get, but it's still pretty nasty, and this requires fairly sophisticated ideas, often from like random matrix theory. Okay, that's pretty much technically all I had. Let me just briefly wrap up. I think there's a lot of interesting directions still to go. So one really interesting question, I think that there have been some talks already at this conference addressing these sorts of ideas. So what we demonstrated is that there's a quantum learning task for which quantum memory provably helps, and that you can demonstrate this on a real quantum computer. But it'd be nice if there's like a classical learning problem, which you can show the same thing for it. That you can show that somehow quantum memory yields asymptotic improvements. So far we don't know how to do this, and there's sort of like a bunch of no-go theorems actually, but perhaps there's something still there. Another natural question is whether or not you can get lower bounds if you have sort of intermediate amounts of quantum memory. So maybe you only have like partial entanglement. What is the right there? We have some sort of very, very recent work on this, but there's also more generally, you know, what if I just allowed some arbitrary quantum memory, not entangled measurements? And for here, our bounds are much worse. Another very natural question is like, what about quantum learning with other constraints inspired by sort of, you know, practical quantum computers, not just quantum memory? Maybe the constraints on like the architecture of the measurements, or constraints on the state itself. Another really nice question is whether or not we can obtain tight rates, not for learning quantum states, but these sorts of quantum channels or transformations and other sorts of things, which I haven't defined, or quantum evolutions. Okay, so that's it. Thank you very much.
Is there any questions? If there's no question, that's actually.
Thanks for the very nice talk. I want to ask, in your analysis, did you put any bound on the width of the tree, the decision tree, or the computational complexity of each? Like you have an adaptive scheme, right? Did you put any bound on the complexity?
No. So in particular, this works for trees of arbitrary, technically even infinite width. Mm-hmm. And yeah, our bound doesn't depend on it. It'd be nice to get like tighter bounds that depend on this, but I don't know how to do this.
Because you know, sometimes putting some computational complexity bounds is very physical, you know. Yeah. Because if you don't put any bound, there could be like in high energy theory, there could be like paradoxes related to the firewall paradoxes.
Well, I mean, it's actually a really great question. Like even like classical shadows, the sort of state of the art measurement uses Haar random measurements, which are very non-computational in some
classical
sense.
shadow isn't an adaptive scheme. It's like each step is sort of independent of each other, right?
That's true. That's true. But they're like the point is that like a lot of these like the state of the art like shadows like this U-sure stuff. All of this is in many ways non-physical. Like it requires very high, like high depth, high quantum circuit stuff. Actually, not for classical shadows in particular, but for a lot of estimates that require these sorts of uniformly random measurements. This is a great question, but we don't know in many ways like the right answers.
Sounds interesting. Thanks.
Is there any questions? If there's no questions, let's ask Professor Jerry Lee again. Next, we have a tea break and come back at 3:30 p.m.